Well, welcome back to the Algebra 2 jungle. Our theme tonight, as we review and get a little closer to our Regents exam, is complex numbers and everything that falls under that category. And once we really feel confident about complex numbers, we can move on and talk about this tricky topic called the discriminant. Now, what is a complex number? Simply a complex number, as we see it here in the form of a plus bi, is basically we're going to take an imaginary number and either add it to or subtract it from a real number. So maybe one example is maybe you take a real number like 5 and you add an imaginary number like 2i, or maybe it could be -6, and then we're going to subtract an imaginary number, something like that. Now technically 7i by itself is considered a complex number. It just means that the real number is a 0. And in even this, if I gave you the number 8, I said that's a real number, but it also falls within the set of complex numbers because what I'm adding is 0 for an imaginary number. So that's a good taste of complex numbers. Now, first and foremost, by definition, the letter I is equal to the square root of -1, which, the square root of any negative causes a real conundrum. And so we've established this definition, and based off of that, the powers of I start off with I to the 0, just like anything raised to the 0 is 1. I to the first is simply itself I squared turns out to be -1, and I raised to the third turns out to be -I. And then from there, it just cycles back, and we say I to the fourth is 1, I to the fifth is I to the sixth is -1, and I to the seventh is -I, and it continues in that fashion. So a lot of times, because of that cyclical nature, we like to draw ourselves a wheel, and we might start off by saying something like I to the 0 is 1, we'll say I to the first power is simply I to the second power is -1, and I to the third is -I, if I can squeeze it in there. And it goes around and around and around. Now, if we want to look at a particular example, let's say my first example is I want to simplify I to the 73rd power. And I'm thinking I could go around the wheel 73 times, and that's very doable, but maybe I want to look for a quicker way. And what we do is we divide that 73 by 4, and we do our long division. And we say, well, 4 goes into 7 once. 1 times 4 is 4. Subtract them, 3. Bring down the 3. And 4 goes into 33 8 times. 8 times 4 is 32. And when I subtract them, I get a remainder of 1. Well, that remainder becomes the new exponent. And so we know that I to the 73rd is really I to the first. Let's make a note of this in our notebook. That remainder becomes the new exponent. And then I to the first is simply I, and that would be my final answer. Now, a lot of the problems we have, though, they have more than one term in them. And let's say, for example, maybe we had a multiplied by I to the 10th power plus b times I to the 24th power minus c times I to the, we'll say, 37th power. And I want to simplify this the best I can, and I've got these unknown coefficients that are being attached to the i's. Well, the first thing I want to do is, if I divide 10 by 4, and I could show my work off to the side, I'm going to get a remainder of 2, so that's I squared. And when I divide the 24 by 4, let's see what I get here. I'm going to show my work. I get 6, 24. That's a remainder of 0. So I got I to the 0 minus c. And I can do 37 divided by 4. Let's see, goes in there 9, 36, remainder of 1. So that'd be I to the first. And I'll simplify this the best I can. A multiplied by -1 plus b multiplied by 1 minus c times I. And that really just turns into -a plus b minus ci, and that's the best I could do without knowing what the values of a, b, and c are. This might be perhaps the most valuable thing I mentioned all night tonight, and that's don't forget about your calculator. And specifically, this button right here, it has the I on it. So if you go second and then hit the decimal, you're going to get your I. And so I'm going to circle that right here. That's your I button. So in fact, if you had a multiple choice question that wanted you to evaluate 5 plus 3i squared, I mean, you could FOIL the whole thing out And that's not a bad idea to do it by hand first, but you could always plug it into your calculator and evaluate it that way to check your answer. So here's a nice little radical to simplify, and we're really good at breaking these down into pieces. And so I'm thinking negative 75 is divisible by negative 25, who's then multiplied by 3. And the square root of negative 25 is 5i. So automatically, once you see this negative sign, you're always going to end up with an I right there. Multiplied by radical 3, and negative 3 times 5i is negative 15i radical 3. Now we're going to focus on solving a quadratic equation. And there's always more than one way to solve a lot of these problems. And I see a lot of the natural tendency is that once we see the squared sign, is we want to FOIL this quantity right here. And that'll give you x squared minus 10x plus 25. And then you would distribute the negative 3. And then you would subtract the 27 over. And then a lot of students would use the quadratic formula. And let me stress, there's nothing wrong with that. But I think that's a lot more work than you need to do. Check out my process. I'm going to try to kill the negative 3 by dividing both sides by negative 3. These cancel, and that gives me the quantity x minus 5 squared equals negative 9. Now from there, I want to try to cancel out the squared sign. In order to do that, I'm going to take the square root of both sides. These rascals cancel, and that gives me the quantity x minus 5. I don't really need the parentheses there. And it would give me plus or minus 3i. Remember, every time we take the square root of something, it should be giving us 2 solutions, not just 1. Now we talked about not really needing those parentheses there. In fact, maybe I'll try to, whoops, it won't let me erase them. We'll pretend these aren't here because I don't really need them. And I'm going to now add 5 to both sides. And let's see, these cancel and I'm left with x equals, and these are not like terms. So the best I could do is say 5 plus or minus 3i. And my 2 solutions are going to be 5 minus 3i is my first solution, and 5 plus 3i is my second solution. Had I done the quadratic formula, I would have gotten the same answer, but it probably would have taken me a minute or 2 longer. And any time that we use a longer process, it opens up the door for some more careless mistakes that we're trying to avoid. Our next example here is significantly more challenging than the previous because now we're working with a cubic equation instead of a second-degree quadratic equation. And we are expecting 3 roots or 3 solutions or 3 x-intercepts, however you want to say it. And in order to identify these, I tried to do factor by grouping at first. However, the GCF in this group and the GCF in that group didn't produce a binomial that was a match, so I couldn't use factor by grouping, unfortunately. So my next plan of action was to take a look at my calculator. And I tried to graph it, and I went to a standard viewing window, and I got something that looks a little bit like this. Okay, it crossed the y-axis at -8, which isn't that important, but what is important is what it did right here. And it crossed the x-axis at x equals 5. Whoops, I take that back. That is not 5, that is 4. It crossed right at x equals 4. And what I see here is because it only crossed the x-axis once, I only have one real solution. Now, why is that? Why did I only end up with one real solution? Because I was expecting 3 solutions. What that means is the other 2 solutions are imaginary or complex solutions. Now, one interesting fact about complex solutions is that they come in pairs. You're either going to have 2 complex solutions, or 4, or 6, or 0, but it's impossible to have 1 complex or 3 complex. And the reason for that is all complex solutions must be conjugates of one another, which is something we'll take advantage of down the road. So here's the kicker. Now, how could I use this to my advantage? Well, what you'll notice is we know that x minus 4 is a factor, right? And so I'm going to do long division using the x minus 4. And let's see what happens, what my quotient is when I perform my long division. Excellent chance here. Let's hit the pause button, crank through it ourselves, and we'll see what our long division gives us. So here I've shown all of my work, and my quotient ended up being x squared plus 2x plus 2. So what we could say now is that f of x is now equal to x minus 4 multiplied by x squared plus 2x plus 2. Now, if it was our lucky day, this quantity right here would factor, but it's not factorable. So my next best option is to use the quadratic formula. So this is a very intensive problem, and I'm going to apply my quadratic formula for this section right here, and it's going to be x equals, starts off with negative b plus or minus the square root of b squared minus 4 times a times c. My a was just a 1, so 2 times 1 on the bottom. X equals negative 2 plus or minus, now 4 minus 8 is negative 4. And here's why it showed up on tonight's video, because the square root of negative 4 is 2i. And then I'm going to use my distributive property for division, negative 2 divided by 2 plus or minus 2i divided by 2. And as I simplify that, I got x equals negative 1 plus or minus I. Notice these are conjugates. In my final, at the end of the day, my solutions are the one real solution I had, negative 1 plus I and negative 1 minus I. Like we said, these two rascals are conjugates of one another, and we ended up with 3 total solutions just like we anticipated at the very beginning. We're going to finish tonight with this topic of the discriminant, and I want to first establish right off the bat why it's helpful to know the discriminant and to be, and why we want to be able to manipulate it and use it. And I'm going to define it this way. I'm going to say the discriminant is a shortcut we use to describe the nature of a quadratic function's roots. To describe the nature of a quadratic function's roots. Of course, instead of the word roots, you could use the word zeros, and I think it's possessive. Okay. And emphasis is it's a shortcut. If we have a light bulb moment and we understand the discriminant, then it can really be a monster shortcut that we use. And we're not trying to create extra work for ourselves. We're trying to create a shortcut here. Now, when we describe the nature of the roots, really what we're trying to decide for the most part is, are the roots going to be real, or are they going to be complex, or I should say imaginary in this case. So are they real or are they complex? And this is a quick way to describe that. Now, as far as memorizing this formula goes, it's nothing really great and grand. Now, consider this. You already know the quadratic formula, right? So let's start with something we already know. Minus b squared, or b squared minus 4ac all over 2a. So the discriminant is simply this rascal right here. That part, the part that falls underneath the radical, not including the radical, is your discriminant. So let's establish that first and foremost. The discriminant formula is b squared minus 4 times a times c. So as we discuss the discriminant, we want to break it into 3 cases. And case number 1 starts off like this. If we evaluate the discriminant, and the answer we get is greater than 0, aka it's a positive number, what we've proven is that that quadratic function has 2 real, and I'm going to add distinct, in other words, they're 2 different numbers, solutions. Alright? And each of those solutions has a multiplicity of 1. That's worth noting too. And the reason I say a multiplicity of 1 is because what I'm going to try to stress is that when I graph this quadratic, it's going to cross through the x-axis. So we've got 1 real solution here and my second real solution there. And again, we said they're distinct because they're going to be 2 different numbers. If this was a negative 1, this might be a positive 3 or something like that. Case 2 is a very rare one, but it happens occasionally, and that's if we evaluate b squared minus 4ac and we get an answer that's equal to 0. What we've proven is, well, technically there's 2 real, whoops, nice if I put an a in there, there's 2 real solutions, but now the multiplicity of that solution is a 2. And what we're really saying is this graph is going to cross the x-axis, or I should say touch it and bounce. All right, so we get a bounce. And a nice fancy term we use is we say that the parabola is tangent to the x-axis. Say that the parabola is tangent to the x-axis. And by this point, you could probably see where we're going here for the third case, and I hope you do. What we're going to say, the third case is if we evaluate our discriminant, b squared minus 4ac, and we end up with an answer that's less than 0, aka negative. And in that case, what we've proven is that there's going to be two complex imaginary solutions. And in this case, when we go to graph the parabola, it's going to never cross the x-axis. It might be entirely below, or it could be entirely above, and that would be dictated on the leading coefficient. We'd say if a, let me start. In this case, a would be less than 1, and in this case, a would be greater than 1, and that would dictate whether it lies above or below. And of course, we could always use our calculator to determine that as well. For our last question of the night, and to see if we understood the three different cases of the discriminant, I pulled off a part 2 question from our most recent Grizzly, and this was definitely a feisty question that a lot of us avoided, and for good reason. We haven't talked about the discriminant in a long, long time. So the question states, determine all values of k for which the roots of this equation, x squared minus 6x plus k equals 0, are complex. Now what we should be saying to ourselves is the moment that we saw the word complex, we're thinking that our discriminant needs to be negative, in other words, less than 0. And I'm going to plug in all the appropriate values. For instance, we've got an invisible 1 here. So I know that a equals 1, I know that my b value is a negative 6, and I know that my c value, in this case, is an unknown value called k. And so as I go to plug them in, I've got negative 6 squared minus 4 multiplied by 1 multiplied by k, and we're going to just try to solve for k. Now, based off the wording, they said determine all values of k, and what they're really implying is that there's more than just one answer. There's not just one value of k, but there's a whole list of values of k that make the roots complex. And as I begin to solve this, we get 36 minus 4k is less than 0, and I subtracted 36 from both sides. And here's a devious little nugget from Algebra 1. When we go to divide by a negative number, the inequality sign must be flipped. And then we're going to say for any value of k greater than 9, such as 10, 11, 12, etc., the values of that quadratic will be complex. Now, I'm always one that likes to check my answers. And so what I might do is, we've got x squared minus 6x. I might pick a random number bigger than 9, maybe 12. And what I'm going to do is I'm going to graph this. And what I'm doing by graphing it is I just want to check and I want to confirm that it never crosses the x-axis. Never crosses. Now, if I did look at this graph and it did cross the x-axis, then what I've done is I've proven that I've done something wrong, okay? And I went ahead and I graphed it, and that was success. It never did cross. It was entirely above the x-axis, so I felt very confident in my answer. And I could try other values right here. You know, instead of a 12, I could put 9.5. I could put a 10, 11, 13, 20, 25, whatever the case might be, as long as it's something that is greater than 9.